this lesson is an extension of the gas laws that we went over the summer. And the first thing that I'm going to talk about is the kinetic molecular theory of gases. And there are 5 different postulates of the kinetic molecular theory of gases. And it helps us in understanding how gases interact with one another. The first one is that gases consist of large numbers of molecules, and they're continuously moving. So they're bouncing off each other, they're bouncing off walls. The next is that if you take all of those molecules of gas and you compress them, the combined volume of all of those molecules, their volume is going to be negligible relative to the total volume in which the gas is contained. So we're going to ignore the volume that the gas molecules actually take up. The third is that the attractive and repulsive forces between gas molecules are negligible. So we're assuming that they don't actually attract each other, they don't repel one another, but they do. They do in fact repel and attract one another, and we'll look at that when we're comparing ideal gases, which we're going to assume in this lesson, versus real gases. The fourth is that when molecules collide with one another, their energy is going to be transferred, so from one to the other. And as long as the temperature remains constant, then the average kinetic energy of the molecules is not going to change over time. And so that's one key relationship that we're going to look at further in just a second, that the average kinetic energy is proportional to the temperature. And the fifth and final postulate is that the average kinetic energy is proportional to the absolute temperature, what I just said for number 4. And so at any given temperature, the molecules are going to have a certain average kinetic energy. So that doesn't mean that all of the molecules are going to have the same kinetic energy. Some are going to have higher kinetic energy, some are going to have lower, but the average will stay the same at a given temperature. So the average kinetic energy, just to re-emphasize this, is proportional to temperature. Therefore, if you have 2 gases at the same temperature, they're going to have the same average kinetic energy. As temperature doubles, then, the average kinetic energy is also going to double. And so, as I just said in the previous slide, by saying average, we're acknowledging that some of the molecules are going to be moving more quickly than the average kinetic energy, while others will be moving more slowly. And so to represent this, if you look, the first thing I want you to notice is the difference in temperatures, 100 Kelvin, 300 Kelvin, 500 Kelvin. Notice that the velocity of these molecules, if they're at 500 Kelvin, on average, the velocity is going to be higher the higher the temperature is. Also notice the fact that the average is not, also notice that while the average might be one specific value, there's a large range of velocities and kinetic energies that the gas molecules can assume. Also notice that that range is much greater when the molecules are at 500 Kelvin versus when they're at 100 Kelvin. So if molecules are at a higher temperature, the range of velocities they can assume are going to be much greater than if they're just at 100 Kelvin. And this diagram is called the Maxwell-Boltzmann diagram. Now look at this second diagram. It shows velocity versus number of atoms. So notice xenon, argon, helium, we're going to assume that they're at the same temperature, so they should have the same kinetic energy. Notice that their velocities are very different, and that's because the formula for kinetic energy is 1/2 mv squared, m being mass. So the higher the mass of an atom, the slower its velocity is going to be. So while they might have the same kinetic energy, their velocities will be different. So the heavier an atom, the lower its velocity is going to be. The lighter an atom, the faster its velocity is going to be. All right, so over the summer we talked about different gas laws: combined gas law, Boyle's law, Gay-Lussac's law, and Charles' law. We're now going to talk about the last gas law, which is the ideal gas equation. So the ideal gas law is PV, the equation is PV equals nRT, P being pressure, V being volume, N being number of moles, and T being temperature. Now R is your gas law constant, which will be given to you, and it's 0.0821 liter atmosphere Kelvin mole. And so the reason why these units are important, the liters tell you that your volume must be in liters, the units for volume must be liters, your pressure must be in atmospheres, your temperature must be Kelvin, and then moles must be moles. By using the ideal gas law, we're assuming that the gases are acting ideally. Specifically, that they do not interact with one another, just like we had seen with the kinetic molecular theory. They're not attracted to each other and they don't repel each other. And then also that when we combine their volume, that volume is going to be much smaller than the volume the gas occupies, meaning that the molecules take up no space. Now, that's not actually the case, and we'll look at real versus ideal gases in just a second. Real gases versus ideal gases. Molecules of an ideal gas are going to be in constant random motion, and therefore they're going to be spread really far apart, meaning that they're not going to be super attracted to each other. So how can we minimize the attraction they would feel? Well, we want them moving as quickly as possible, meaning we want a high temperature, and we want them as far apart from one another as possible, which means low pressure. So if you have high temperature and low pressure, under those conditions, gases will act as ideally as is possible. Now, when these conditions are not met, you're going to have a real gas. And if you use the ideal gas equation, when you have a real gas, you're going to end up with some errors. And so we're going to be dealing with real gases in labs, and so we're just going to have to accept there is going to be some error because we do not have ideal gases. So the purpose of these graphs right here are to reiterate the importance of high temperature and low pressure. So notice as pressure increases, as you move from left to right on that graph on the left-hand side, all of those gases deviate more and more and more from the ideal gas, which is just a solid line at 1. Similarly, for temperature, as the temperature decreases, then the gases will act less and less ideally because they deviate the most from that ideal gas line of 1. So you want high temperature but low pressure. And finally, molecules are more likely to deviate when their intermolecular forces are strong. So yes, you want low pressure, high temperature, but another thing that influences whether or not they're acting ideally is the strength of their intermolecular forces, meaning if you have two atoms that have London dispersion forces, you want the one that with the weakest London dispersion force, and that one would deviate the least from an ideal gas. Something with hydrogen bonding, if it's a gas, would deviate the most from acting like an ideal gas, while something with London dispersion forces that's really, really small would deviate the least. So in this problem, I'm given volume, I'm given pressure, I'm given temperature, and I'm asked to solve for the number of moles of oxygen. And so I'm going to be using the ideal gas law, so PV equals nRT. Okay. Remember, your R value, your constant, is 0.0821, and the units are liters times atmospheres over Kelvin times moles. Okay? So the pressure must be in atmospheres. So I have 2.3 atmospheres. Notice my volume must be in liters. So right now I have it in centimeters cubed, which is equivalent to milliliters. So I've got to divide that by 1,000 to get it into liters. So I have 0.0026 liters. And I'm going to set that equal to, well, I'm solving for my number of moles, so N, times my R, which I have, which is given to me, so 0.0821, and then times my temperature. So my temperature right now is in Celsius. I need to convert that into Kelvin, and when I do that, I get 299 Kelvin, okay? And so when I solve for my N, I multiply 2.3 by 0.0026, divide that by 0.0821, divide that by 299, and what I end up with my answer, having 2 sig figs, I get 2.4 times 10 to the negative 4th moles. Okay, so that's the first part of this problem. The next part of this problem asks me how many grams of oxygen is this? Well, I know how many moles I have. I have 2.4 times 10 to the negative 4th moles. And so I need to convert that into grams. So I'm going to put the moles on bottom, grams up top. This is molar mass. So since I have O2, the molar mass of O2 is going to be about 32 for every 1 mole. And so when you multiply this, what you should end up getting for the mass is 0.0078 grams. So there's my mass. I'm almost done. I have one last question, and it asks, what's the density? Remember, density equals mass divided by volume. So here I know my mass. It's 0.0078 grams. And I'm going to divide that by the volume. And the volume I was given at the beginning of this problem was 2.6 centimeters cubed. And I'm just going to keep it like that. I don't need it in liters for this part. Okay? And so when I do that division, what I end up getting is 0.0030 for 2 sig figs, and it's grams per centimeter cubed.